Hi and welcome. So today we will be seeing heap in Java. Okay, Java implementation of heap. Before that, let me explain you some concepts of heap. So what is a min heap? In a given almost complete binary tree or a complete binary tree, at every node root is minimum or equal compared with its children, then it is a min heap. And if the root is maximum or equal compared with its children, then it is a max heap. Okay, let me give you an example. It will be very clear. So the first example is of min heap. Here you can see the root is smaller than its children. 20 and 50 are greater than 10, correct? Then every node should be a min heap. Every node should be a min heap in itself. Fine. So 20 a min heap? As we can see, 70 and 80 both are greater than 20. So yes, 20 is also a min heap. Next we can see that here 50 is also in a min heap because 50 is smaller than 60 and 90. So if the root is smaller than its children, then we have a min heap tree. Fine. And always heap are almost complete or complete trees. Okay. Then what we can see here is, and the next point to note is, the leaf are always min heap. Okay. The leaf are always min heap if we are seeing a min heap tree. And the leaf here are always max heap if we are seeing a max heap tree. Fine. So leaf are always min heap or max heap depending on the tree that we are dealing with. As you can see here, 90 is a max heap. It is satisfying the property of max heap because 90 is greater than 80 and 90 is greater than 70. Next we can also see that, as you can see here, 80 is greater than 10 and 30. Now is 70 a max heap? Just think, is 70 a max heap, meaning 70 is 70 satisfying the max heap property? Just think. So yes, 70 is satisfying the max heap property because 50 and 20 are greater than 70. And I have told you every leaf node is always a min heap or a max heap depending on the tree we are dealing with. So these are the examples of min heap and max heap tree. Next we will be seeing array representation of max heap tree. Okay, so this is my max heap tree that we have seen just now. So what will be the array representation for this? Okay, so this is the array representation, and here we can see that the 90 is first, then its children 80 and 70 are next, then their children 10, 30 and 50, 20. So this is nothing but, you can say it is a level order. It is nothing but level order. As you can see here, first is 90, so here also first is 90, correct? So here it 80, the second level, this is the level 0, first level 0 elements, then level 1 elements, and in last the level 2 elements, correct? Level 0 elements, level 1 elements, and level 2 elements. Fine. You can also use the indexes. So this is at the index 1, this is at index 2, this is at index 3, this is at index 4, this is at index 5, 6 and 7. Okay, using these indexes in our array we can know what are the parents, who is the parent, and what are the childs of a parent. Okay, so if I want to know who is the parent of 80, so using the indexes in our array without drawing the tree, we can know who is the parent of 80. Okay, for example, we want to know who is the left child of 70. So using the index of our array without drawing the tree, we can know that who is the left child of 70, that is 50. Similarly, we can know who is the right child of 70. Similarly, we can know who is the right child of 70. Correct? Only using these indexes without drawing the tree. If someone gives you a max heap array representation of a tree, fine. So you can know who is the child, who is the parent, fine. Or you can directly draw the tree and tell them. But in our code, if we want to know who is the left child and who is the right child, then these are the formulas. These are the formulas. So the left child is given by 2 into I. The left child is given by 2 into I. The right child is given by 2 into I plus 1. 2 into I plus 1. And the parent is given by the floor of I divided by 2. The floor of I divided by 2. So this is the left child, right child, and the parent. And remember, this I is starting from 1, not from 0. Okay. So the index is starting from 1. So these formulas are for index starting from 1. Fine. So let's take some examples here. So if we take 80, so who is the parent of 80? So 80 is at index 2. So parent of 80 is 2 by 2, that is 1. So who is at index 1? 90. So parent of 80 is 90. That is correct. So let's say we are taking 10. We are taking 10 and we want to know who is the parent of 10. So index of 10 is 4. Correct? And so parent of 10 will become 4 by 2, that is 2. Who is at index 2? It is nothing but 80. So yes, the parent of 10 is nothing but 80. Now for example, I want to know who is the right child of 70. Who is the right child of 70? So for 70, index is 3 and put it into the right child's formula. So 2 into 3 plus 1 gives me nothing but 7. So see the index 7. Who is at the index 7? It is nothing but 20. So the right child of 70 is nothing but 20. Next we can see one more example. For example, we want to know who is the left child of 80. Who is the left child of, for example, 90. Okay, we have seen of 80. So who is the left child of 90? So the index of 90 is nothing but 1. Put it into this formula. 2 into 1 will become 2. So the left child of 90 is the element at index 2. So that is nothing but 80. So as we can see in the tree also, the left child of 90 is 80. So using these three formulas, you can know who is the left child, who is the right child, or who is the parent of a particular node. Okay, so write these formulas down. They are very important formulas, and some MCQs are also solved using these formulas directly. Fine. So after this, we will be seeing properties of complete binary tree. Now you have seen these properties before also when you were learning about complete binary tree, but in heap also we use them, therefore I am revising them. So the first property is height of a node equals to max distance of that node to the leaf. We know that. Okay, I will be showing an example also. Then height of a tree is nothing but the height of a root node. Next one is max number of nodes in complete binary tree for a height h is given by the formula 2 to the power h plus 1 minus 1. Okay, and the min height of node and the minimum height that is given for nodes n is given by the formula of floor log n. You all know these formulas because we have seen them in complete binary tree videos also. So for example, in this tree, if we see that the height of node 80 is nothing but the max distance of that node to the leaf. So height of node 80 is, in the left child it is 1, in the right child also it is 1. So the maximum distance is nothing but 1. So the height of 80 is 1. Height of 70 is also 1. Height of 90 on the other hand is 2. So what is the height of the tree? Height of the tree is equal to height of the root node, which is nothing but in this case 2, because the height of the root node is 2. Correct? Now for this case, for example, my maximum height is 2. So maximum nodes can be in a complete binary tree. Just put that into this formula. 2 to the power of 2 plus 1 will give me an 8. 8 minus 1 will give me a 7. So total nodes become 7. So 1, 2, 3, 4, 5, 6 and 7. Yes. So this formula is correct. So we got our 7 nodes. Now if we have 7 nodes, then what will be the minimum height of the tree? So the maximum height of a tree can be a skew tree, correct? So this is a skew tree. So maximum height can be this. But what can be the minimum height? So the minimum height is floor of log to the base 2 of 7, correct? So that will be nothing but 2, because we all know 2 to the power of 3 is 8, but 7 is less than 8. So it will be 2 to the power of 2 because we are taking flow. So 2. So height is 2. This is also correct. So this was just a small revision of properties of complete binary tree. Now the next property which we will see, it is actually important. It is very important. Also in this properties, what I also here, this is log n, correct? The minimum height is log n. So a max tree height is also log n. A max tree height is also log n. The reason being, max tree is always a complete binary tree or a almost complete binary tree. Okay, I am taking examples of max tree. The same properties applies to min tree also. Fine. Since for nodes n, the minimum height of a complete binary tree is log n, therefore and max tree or min tree are always complete binary tree or almost complete binary tree. Therefore the height of a max tree or a min tree is always log n. So you can make that point. The next property which we are going to discuss is a really important property for our heap. So the next property is, in a complete binary tree or almost complete binary tree, once a leaf start, then all will be leaves. Okay, so for nodes n, 1 to floor of n by 2 are non-leaves, and floor of n by 2 plus 1 to n are leaves. Let's take some examples. So for example, in this tree, let's take the indexes 1, 2, 3, 4, and 5, correct? So let's take, so n value is nothing but 5, n value becomes 5. So for value of n, what are the non-leaves? 1 to 5 by 2. 1 to 5 by 2 means, and the floor of 5 by 2. So 1 to 2 are my non-leaves, and I think from 3, that is 2 plus 1, 3 to 5 are my leaves. So let's see. So 1 and 2 are my non-leaves, and 3, 4 and 5 are my leaves. So where are my leaves starting? Leaves are starting from index 3 and they will continue to n, that is 5. So once a leaf start, then all will be leaves if we are talking about complete binary tree or almost complete binary tree. Let's take one more example. So here, let's number them first. So it is 1, 2, 3, 4, 5, 6 and 7. So n becomes 7. N becomes 7. So 1 to 7 by 2, the floor of 7 by 2, which will be nothing but 3, are non-leaves, and from 4 to 7 are leaves. Let's check. So 1, 2 and 3 are non-leaves, and 4, 5, 6 and 7 are leaves, correct? So just keep this in mind. This is very important for heaps. Okay, so what was this property? Once a leaf start, then all will be leaves. And the second one is 1 to floor of n by 2 are non-leaves, and floor of n by 2 plus 1 to n are leaves, correct? So 1 to 3 are non-leaves, and 4 to 7 are leaves. So this was a very important property, so just keep that in mind. So now let's see build heap and max heapify. So what these two terms mean. So this is, for example, my tree, and this one is the array representation of that tree. So now what you have to do is just see if my array representation is correct or not. Okay, just apply those formulas, that is right child, left child, and the parent formula, and see if this array representation is correct or not. Fine. So you can easily do that. Therefore, I am asking you to do it. The next point which I am going to explain is, just now we have seen where the leaves start and where the non-leaves end, correct? So for example, here we have 10 nodes, so n value becomes 10. So n value becomes 10. Fine. Since n value becomes 10, so from 1 to 5 becomes my non-leaf, and from 6 to 10 becomes my leaf, Okay, just now we have seen this formula. So let's see, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, 9 and 10. Fine. So as you can see here, from 1 to 5 are my non-leaves, 1, 2, 3, 4 and 5 are my non-leaves, and 6, 7, 8, 9, 10 are my leaves. So yes, the formula is correct. Fine. So next what I want you to do is just see if this is a max heap or not. Is every node satisfying the property of max heap or not? We all know that leaves are actually always satisfying the property of max heap or min heap in any case. Okay, so 6, 13, 2, 9 and 15 are always satisfying the max heap property. So we need to check for the non-leaves. So is 1 satisfying the property? No, because 17 and 10 both are greater than 1. So actually 17 should be there, but it is 1. So this tree is not my max heap tree. We need to heapify it. We need to what? This is a term. We need to heapify the tree. We need to heapify actually every node. Okay, here 17 is also not a max heap. As you can see, as you can see here, 3 is not also a max heap because 13 is greater than 3. So we need to heapify this node also. Fine. We need to heapify this node also because 15 is greater than 10. So the heapification process, meaning changing every node to a max heap, changing every node such that that node now satisfy a max heap property, that process is known as heapification, and building the whole tree, this whole heap, is known as build heap. So at every node, it is a function build heap that will apply max heap property. Okay, at every node, it is a function build heap that will apply max heapify algorithm. Fine. So the build heap method will apply the max heapify algorithm in every node, at every node, because every node has to satisfy the max heap property. Okay, so from where build heap will start? So we do not need the build heap in our leaves. Okay, because we do not need heapification process here. The heapification process has to start from 8, that is the first non-leaf. Okay, we are starting from bottom, and the first non-leaf we encounter is 8. So the heapification process starts from 8. Okay, so the build heap function that we will write also, the build heap function, a for loop will start, and that for loop will begin from where? It will begin from n by 2, the floor of n by 2 down to 1, that is I minus minus. Okay, from n by 2 to 1, that is I minus minus. So first it will heapify 8, then it will heapify 3. So this much tree is built, this much heap tree is built. Then it will heapify 10. So now this much heap tree is built. Then it will heapify 17. So now this much tree is built. Only one node is left. And then at the end it will heapify the root node also, and our whole heap tree will be built. Fine. So the heapification process, that is a build heap, will begin the heapification process from the first non-leaf node from the bottom. The first non-leaf node from the bottom. And how we will get that? Using this formula. We have seen that where the non-leaves end and the leaves begin. Fine. So let's now begin the heapification process. So my eye will point to this 8. So my eye is now pointing to 8. What I will check the left child and the right child. I will check the left child and the right child. Now since right child is not present, it will only check the left child, and it will check the values, whether 8 is smaller or 8 is greater. Since 8 is greater, there is nothing to be changed here. There is nothing to be changed here, and we will have one more variable, largest. Since nothing is changed here, so the largest will now starting point to 8. Okay. Now in this whole scenario, the largest element that I have got is nothing but at index 5. So variable largest will start pointing here, okay. In every scenario, whatever will be our largest value, the largest variable will start pointing to that index. The largest variable will start pointing to that index, the largest values index. Fine. So we do not need to swap anything. If this was smaller, we needed to swap it, but we do not need to swap anything. Since now we know that 8 is greater than 6, that means the node 8 is actually following the property of max heap. Now we can move on to node 4. Because I minus minus is there, so what we can do is, it will start from 5, then minus minus, it will go to 4. So now I equals to 4. So now I will start pointing here. Let's see that. So now what we can see is that I will start pointing to here. The numbers are 1, 2, 3, 4, and 5. Correct? And this is 6, 7, 8, and 9. So now I will start pointing to 4. Now what will happen is, this will check with its left child and this will check with its right child. So is it greater than its left child? No. Sorry, yes, it is greater than its left child. Is it greater than its right child? No. 13 is a larger one. 13 is a larger one. So what will happen is, when it will check which is greater between 3 and 2, 3 becomes the greater. So larger, that variable large, will start pointing to 3. The largest variable will start pointing to 3, that is the index 4. After that, it will check whether 3 is greater or 13 is greater. Now what it will check? That 13 is greater. So largest will now start pointing here. So largest is the greedy one. Whichever is greater, largest will start pointing to that index. Whichever is greater, start pointing to that index. So the largest value is nothing but 9, and I value is nothing but 4. After that, we have to swap largest and I. Just swap at the end largest and I. Correct? Largest and I. Once you swap it, so 13 will be swapped with 3. So 13 will be swapped with 3, and we have to call max heapification again, because this is nothing but recursion. So we have to call the max heapification process again on that 3. But since it is a leaf is always follow the property of max heapification, that is a max heap property. So we will just simply return. So the next tree that we will get here is this one. So 13 and 3 are swapped. And when the heapification process is called on 3, it will see that it is a root and it will simply return. So this one is done. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this one is done. They both are heapified. So now what build heap will do is, it was I equals to 4. Now I minus minus, so I will become 3. Once I becomes 3, I will start pointing here. Now what it will check? It will check for its left child and it will check for its right child. Correct? So both are present. So it will check for its left child. Is 15 greater than 10? Yes, it is greater than 10. So the largest will start pointing here. The largest will start pointing here. So the largest now have the value of 6 and I has a value of 3. Then it will check among these two. Now it will check among these two. Okay, so it will check from 15 and 19 who is greater, because largest, what it says that I want to point to the largest value. Okay, so you have to check for every possible values. So now since largest is 15, so it will check with this. So 9 is smaller, so nothing will happen. Largest will keep pointing here, and at the end largest will be swapped with I. So that last line, that is swap largest and I, that will perform, and 15 and 10 will be swept. 15 and 10 will be swept. So 13 is done. This node is done, heapification. This node is done, heapification. This node is done, heapification. Now build heap will make I pointing here. Build heap will make I pointing here. So 1 and 2, 3, 4, 5. Fine. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So now what will happen is I will start pointing here, and again the same process. Now you know what is the process. Now you know, na, correct, what is the process. What we will do, just think about it. We will check with left, we will check with right, correct. Now suppose left is smaller, so where now the largest will point. Now tell me where the largest will point, whether the largest will point to the index 2 or the largest will point to index 4. Just think about it, where the largest will point. So the largest now will point to nothing but 2, because 17 is greater than 13. Fine. Now the largest will be compared with the second one. Same as here, the largest was compared from this, correct? So 17 will be compared with 8. So who is greater? 17 is greater. So this is heapified already. This is heapified already. So nothing will be swept. Nothing will be swept. So we have swept 3 from 13 from here and 15 and 10 here, and nothing are swept till now. Only these two are swept. 8 is not swept and 17 is not swept. Now as you can see, the left hand side, that is the left subtree, is actually following a min-heap property. This whole left subtree is following the the max heap property, and the right subtree is also following the max heap property, correct? So this is following the max heap property and this is following the max heap property, but our one is not following the property. Our one is not following the property. That is, the root now is not following the property. Only the root is remaining. Because of the root, we cannot say that this tree is a max tree. We cannot say that this tree is a max tree. Fine. So let's now heapify our root. Now what build heap will do, I equal to 2 is heapified. Now I minus minus, so I will now start pointing here. So let's now heapify 1, correct? So when 1 is heapified, now when I start pointing to 1, what will happen? Now tell me what will happen. Now you know what will happen, because I have explained heapification for every node. So you should know what will happen with 1, correct? So what will happen is 1 will now start this index 1 and value 1 will now check its left side and the right side. So in the left side, when it checks, it sees that 17 is greater than me. 17 is greater than me. So where the largest will start pointing? Largest will always point to the largest element index. So largest will simply become 2, correct? And I is simply 1 till now. After that, since largest is start pointing here, this will be compared with its right hand side. This will be compared with its right hand side. So as we can see here, 17 is greater than 15, so largest will not change. Largest will not change. So what will change? It's simple. Now at the end it will swap largest and I. It will swap largest and I, and 1 and 17 will be swapped. As you can see here, the 1 and 17 are swapped, and I was 1 and largest at the end of our process was 2. I was 1 and the largest at the process was 2. So largest was still here. Largest was still here. So till now what was happening is, whenever I was swapping, the element was becoming a leaf. The element was becoming a leaf. So 3 became a leaf, 10 became a leaf. So we did not have to do another heapification for this node. But as I've told you, this was a recursive process. So what is happening here is, whenever these elements are swapping, the heapification is called again. But at that time it is saying that this 10 is nothing but a leaf node. Since it is a leaf node, it is always satisfying the property, so nothing is happening. But here what we can see is 1 is not a leaf node. This is not a leaf node. This is an index 1, this is an index 2, this is 3, 4, 5, 6 and 7, correct? This is 8, 9 and 10. So what will happen is this max heapification function is a recursive function. It will call the max heapification again, and it will pass the array, because this is nothing but an array representation. We are doing every swapping in array only. And next is it will pass largest. It will pass largest. Okay. So it is an array and it will pass largest. Now what I value becomes? Now I value becomes whatever value the largest was storing, that is nothing but 2, and what array is array. So this will be stored. Nothing will happen here. The changes will be updated inside the array, and I will store largest, and that is nothing but 2. So I will now start pointing here. I will now start pointing here, and we do not have a largest now because the recursion is again starting. So I will start pointing here. So next the same process will start again. It will check with 13 and it will check with 8. Who is greater? 13 is greater. So largest will start pointing to 13. Largest will start pointing to 13. Now it start pointing to 13. 13 is greater than 8, so it will remain here and it will swap. They will swap each other. After swapping, this will happen. After swapping, this will happen. So 1 and 13 are swapped. Correct? Largest still pointing here. Largest is still pointing here. So again the max heapification process will be called on 1. Again the process will be called because still this is not a leaf node. So we have to check for heapification again. So again when the max heapification process is called, what will happen? It will pass the array and the largest. It will pass the array and the largest. So now I will begin with, this is 1, 2, 3, 4. So I will now become 4 and 5, 6, 7 and 8, 9 and 10. Okay. 8, 9 and 10. So now I will become 4 and array will be updated. So now I start pointing to 4. I start pointing to 4. Correct? Now this again the heapification process will happen. It will check with its left side and it will check with its right side. So it's 2 greater than 1. Yes. So now array start pointing. So the largest start pointing here. Fine. Now is 2 greater than 3. No, 2 is less than 3. So largest will leave here and it will come here. So largest is greedy. What largest will say, whoever is the largest element, I will be pointing to that element. So 3 is the largest element in this case. So it will start pointing here, and after that the I and largest will be swapped. So our next tree will be this. So 1 and 3 are swapped. So 1 from the root came to the leaf. Okay, and this was its path where it came from. In the middle, it was swapped with 17, 13, 3 and 1. Now you can see that the whole tree is max heapified. The whole tree is max heapified. So 17 is the largest element of 13 and 15, correct? 15 is the largest element for 10 and 9, correct? 13 is the largest element for all subtree, as you can see. So 3 and 8 also. 3 is the largest element for 2 and 1. 8 is the largest element with 6. So we have our max tree. So this was how a max tree happens. So what happens is, first is a build heap. Build heap will start from the first non-leaf node and it will go to the root, and it will go to the root. What max heapification does, it takes an array, and a value of I, the index pointer, and in the end, because it is recursion, what it will do, it will call max heap again with array and the largest. Fine. And here are the base conditions, whether it is a leaf or not. That is a base condition. What can be the another base condition? That since 8 is greater than its left child and it has no right child, we have to check that, and its 8 is greater than 6, so we can return, because we do not have to swap anything, so we can return it here only. Why? To perform all the operations. So these two can be my base conditions. Next, what we have to check? We have to check for the left side, then we have to check for the right side. In the middle, we have to update our largest. In the middle, we have to update our largest accordingly. Fine. So now what we will do, we will see the code for this. We will see the code for build heap. We will see the code for max heapify and how to create a heap class in Java.